Example 5.10 or 6.10 for the given textbooks. For details, please see the description below. A refrigerant R134A is to be cooled by water in a condenser. The refrigerant enters the condenser with a mass flow rate of 6 kilograms per minute at 1 megapascal and 70 Celsius, and leaves at 35 Celsius. The cooling water enters at 300 kilopascals and 15 Celsius and leaves at 25 Celsius. Neglecting any pressure drop, we need to determine the mass flow rate of the cooling water that is required and to determine the heat transfer rate from the refrigerant to the cooling water. In order to solve this problem, one of the first things that you need to do is to make sure that you have the correct control volume. Notice that we take the control volume to be the entire system, and therefore we have the refrigerant entering, the refrigerant exiting, we have the cooling water entering, and the cooling water exiting the system. So when we do a mass analysis and an energy analysis, we need to account for the 4 different points in the control volume. We are going to assume that this is an steady system. Then we simply could say that the mass balance is simply the mass flow rate going in is equal to the mass flow rate leaving. And then by the control volume, we simply said that the mass going in for the refrigerant has to be equal to the mass going out for the refrigerant. So that means that mass m.3 is equal to m.4. And doing the same analysis, we do it for the water, is equal to m.2. And the reason we're allowed to do this is because notice that there is no there is no mixing between the refrigerant and the water. So each one of them is independent. We're going to do the same thing for the energy. The rate of energy going in is equal to the rate of energy leaving. Once again, there is a steady condition, and we are going to neglect the change in kinetic energy and potential energy. Therefore, since it's an open system, the only thing that we have is the change in enthalpy. Once again, because we have a control volume that crosses for the 4 openings in this control volume, and energy does cross from the water into the refrigerant and vice versa, we are going to add both of them. So we simply set the mass flow rate at 1, H1, plus mass flow rate at 3, H3, those are the ones going in, is equal to the mass flow rate leaving for H2, plus mass flow rate for H4. So this is for the water, this is for the refrigerant entering, and this is for the water and the refrigerant exiting. Since we already said that the mass flow rate for the refrigerant and the water remain constant respectively, we could simply set M1 for the water is equal to simply H1 minus H2, and in the same case we simply set M3 is equal to H4 minus H3. And then this is going to be the mass flow rate of the water, and this is the mass flow rate of the refrigerant. Okay, the next step is to be able to get the values for the enthalpy. We're going to start with water. We need to double check the phase of water. Therefore, we go to table A5 and evaluate the information at the pressure of 300 kilopascals. So if we go to 300 kilopascals, we see that the saturated temperature is equal to 133.52, and that saturated temperature is greater than both of the conditions that we have for water, one at 15 Celsius and the other one at 25 Celsius, which means that at the 2 points in the control volume, water is going to be considered to be compressed liquid. Since that is the case, we're gonna go now to table A4 for the particular temperatures, and we simply see that the temperature that we start with is going to be 15 Celsius. So we're gonna go to 15 Celsius and we're going to evaluate it at the saturated liquid point, which means that we have an enthalpy of 62.982, and then we go for a temperature of 25 Celsius, and once again we evaluated the enthalpy at the saturated liquid point, which is 104.83, both to be in kilojoules per kilogram. Now we have to do the same process for the refrigerant. For that, we go to table A12 and we evaluate the quantity at 1000 kilopascals, which is equal to 1 megapascal, and then we see that the saturated temperature is equal to 39.37. This means that the refrigerant entering the system, which is at 70 Celsius, is higher than the saturated temperature. It means that it's a superheated vapor. However, the temperature leaving the control volume is at 35 Celsius, which indicates that the refrigerant behaves as a compressed liquid. So for point 3, since it's a superheated vapor, we go to table A13. We see the table for 1 megapascal, and we go for 70 Celsius, and then we go across, and we find that for the value of the enthalpy, we have 303.87 kilojoules per kilogram. For point 4, since it's a saturated liquid, we go to table A11, and then we look at the temperature that we have to be 35. Notice that we do not have 35, so we simply have to do an average between those two values, and the two values that we have are going to be between 99.41 and 102.34, and the average between those two values is going to give us 100.88 kilojoules per kilogram. Now that we have all the values of the enthalpy, we're going to solve this equation for the mass flow rate of water, and that is simply going to be the mass flow rate for the refrigerant and the difference between H4 and H3 divided by H1, H2. And once you substitute all these values into this equation, we find that the mass flow rate of water is equal to 29.1 kilograms per minute. To determine the heat transfer from the refrigerant to the water, we need to change the control volume. In order to do that, now we're going to use the control volume to be drawn like this. If we do that, what we're going to be able to do is evaluate either the heat that is gained by the water or the heat that is lost by the refrigerant. Now that we have this control volume, we're going to evaluate it as the amount of energy going in, amount of energy leaving, and also the amount of energy that is lost from the refrigerant into the water. So we write the balance of energy. The rate of energy in is equal to the rate of energy out, and then in this case the amount of energy going in is going to be the mass flow rate at 3 H3, and what is leaving is going to be mass flow rate at 4 H4, and the heat that is being lost from the refrigerant into the water, we simply gonna be taking it to be Q dot out. Notice that the amount of energy lost from the refrigerant to the water is exactly the same amount that is gained by the water in order to have conservation of energy. So for us to be able to find the amount of rate of heat leaving the refrigerant, we simply solve for Q dot out, and we simply do M3, which is exactly the same value of M4. M dot 4 is going to be H3 minus H4 is equal to Q dot out, and this is equal to 6 kilograms per minute, and the values that we have are 303.85 minus 100.87, and this is kilojoules per kilogram, and once again this is Q dot out, and this, if we multiply these values, this is going to give us 1217.8 kilojoules per minute. and that is the value of Q dot out. Once again, that is the amount of energy, amount of heat rate transfer from the refrigerant into the water. If you had done the analysis of the amount of heat transfer gained by the water, it would have given you exactly the same result.